Hi everyone, I'm Fran, and with an amazing team, we start and create a project for Omdena Argentina chapter. It was based on the problem of matching analysis for monitoring land use change, deforestation, and urban expansion in Córdoba, Argentina, as an MVP and a starting model. The idea that we've been having in mind, it was to create like an interactive map viewer for non-tech users to be able to map deforestation, just creating polygons and saving different spaces, and even with more search queries, advanced search queries, and giving some advanced analytics like, hey, when it was a deforestation, in which times, what happened after the deforestation, urban development, or what. The idea also was to be real-time processing almost, so using Sentinel data that has 5 days intervals, and trying to combine multiple data sources and multiple maps from Google Earth Engine. So that was the idea. This started in July. I was alone in my room starting this idea, and then we, in a couple of months, we be an amazing team working together every Saturday, every weekdays in our free times to make this happen. A special mention to Pascal that he's not here today, and I see a lot of people that is not here today and should be here because they did an amazing work. So I'm happy with my final goal. It was to learn and to new people, and that was achieved for far away. And the next one, it was to create the solution, and we are more than happy with what we will come. Okay, without further ado, let's start the presentation with the different teams.
Thank you, Fran, and welcome everybody. I am Mujtaba, and I co-lead the data pre-processing and analysis and model team with David, and some of my team members' name is written here, and many more contributed to this project. And I will start by especially mentioning and thanking to Pascal. He was a real inspiration in this teamwork, and he did a lot of amazing work. So we can move to the next slide. So our task was to study the deforestation based on two important parameters, time and also the area. So the overall general pipeline is given on the top in block diagrams, and our team's process is given in pre-processing. And the objective of this team was to create a pipeline which can refine and access the Sentinel-2 data provided by the different timelines by the user, and also on the location. And different steps and challenges were involved. When I started this work, it was my first chance to see Sentinel-2 images. It looked straightforward, but when we dive deep in, there were many steps and many things to learn and understand. So next slide, please. So the challenges which we faced is that we were using Sentinel-2 image, and as Fran said, that it had 5 days visit time to a specific location. So if a user chooses some specific date, we might not have image available on that date. So first of all, we need to had a composite type image, like we try to make multiple images into one image. So this was the last step written in this challenge. The first step was to get a very good, reliable image which will be free from cloud. So we tested for cloud coverage, and we make a threshold of 35%, which worked well. And then we were getting the satellite images at two different times, at T1 before the tentative deforestation, and T2 after the tentative deforestation. So it was required to have some kind of geometric registration. So we analyzed the same pixel for T1 and T2. Then, as we were using open source softwares and our own limited computational powers, so large image handling could be an issue. So for that, we try to use a tiling method, that we try to divide a large image into small images. And finally, we did some noise reduction and Gaussian blur to have a final very good representative image. The steps are highlighted in the bottom block diagram. One of the steps which we did was the forestation check. It is currently not the part of pre-processing pipeline, but the code is available and we did it successfully. And it can be integrated in next steps. Next slide, please. So our pre-processing steps, so next 2 slides, I will briefly comment on the results which we did. One is that the tiling of the images. The example is given here that if user chooses some large image, so we can dial that image and we can process it parallel for effective pre-processing, applying all the steps I mentioned in my previous slide. Next slide. So this is the last slide of our pre-processing steps, and it just summarizes some of the steps which we incorporated. For example, if you start from the extreme left side, if the user selects that area which is being represented by this red block, first we will check if the tiling is required for that or no. If the tiling is not required, then we will proceed for the pipeline steps. If it is required, then the tiling will be done. And then the next 4 figures represent the cloud presentation. We can have some images like 1, 2, or 3 with minimum or no cloud, and we can have an image with a lot of cloud, as represented by the extreme right image in the top row. So based on our automatic process, the appropriate images will be selected, and then a median composite will be prepared using composite method and also Gaussian blur method. And after that, in our pipeline, we tentatively checked with NDVI, like normalized difference vegetation index, to check the vegetation. And this was also used for forestation check. And if everything goes well, then the images at 2 times, like T1 and T2, will be handed over to the next process, to the next team, which will be model processing team. So this is the work, short summary of our team's work. Thank you.
Great, thank you, Mujtaba. That was great. So I'm Julieta. I'm part of the pre-trained model and experimentation team. This is the people that are part of our team: Jair, Naudita, Suraj, and myself. Can we go to the next slide, please, Fran? Thank you. Okay, so our objective was, at the beginning, it was pretty clear. We know we had to find a pre-trained change detection model that could work on satellite forest images. It could work on Sentinel, on Landsat. Either way, we could work with that. So we knew we needed images from the same geographical space, from T1 and T2 being 2 different times, like a before and after deforestation. So we could create a change mask that would be the outcome of the model, right? So that's the idea we started this challenge with. Let's go to the next Fran. Thank you. And also, like Mujtaba said, for their team, at the beginning, it was pretty straightforward. We thought it was going to be relatively easy, and it ended up not being so once we started testing the models, because we first started with the literature review for change detection models. That was what we thought was going to be what would lead us through this challenge, right? There are models that could take 2 images of the same geographical space on 2 different times, and could give us a change detection mask. So we tried a lot of these models, some based on transformers. We tried segment any change, which was again from the SAM model, very different types of architectures, and we found that they were pretty difficult, first of all, to replicate the code that we found online. There was not much documentation, And then for most of these models, they were all trained on very high resolution images and mostly focused on urban areas. So then we pass to our second part of or stage of this project on the next slide. We started working on barely like segmentation models, leaving behind this idea of directly using a model that could lead us to a change mask, just using segmentation models on these 2 different times images and see if we could by ourselves get this change detection mask, right? But the outcome was pretty much the same. There are really little amount of models that are pre-trained on satellite images. And the truth is that we didn't have a large enough data set ourselves to test any of this or like fine-tune any of these models. We had a very small sample of images like annotated on the deforestation that we were working with. So finally, we ended up working with unsupervised model. Yeah, next. Yeah, thank you. Unsupervised methods. We tested some, and again, we were having not too good results on our sample images. That were a few amount of those images. And again, we didn't have a large enough data set annotated to test these models, which is like why we realized that if we wanted to use any of these approaches, we would need a lot more time and effort to create a data set that was annotated enough to either fine-tune or get to a model that would work on this. So that's how we ended up working on this combination of change vector analysis and the dynamic world dataset that Haid is going to tell you about next.
Hi, thanks. Well, as you mentioned before, due to limited resources and a lack of training data, we use the land cover probability maps from the dynamic world dataset. This near real-time dataset is ideal for leveraging all the capabilities of the World Air Engine API, since it is continuously updated with each new Sentinel-2 image acquired. The dynamic world dataset includes 9 different land cover classes: water, trees, crops, grass, through the vegetation, shrubs, built areas, bare soil, and snow ice. However, during our experiments, we found that the tree class is similar to the forest areas of the Córdoba region. So we use this class for the deforestation task. Next slide, please. Okay, regarding change detection, the approach we applied is binary change detection, or BCD, using change vector as a mapping function. BCD is a simple technique that compares images from 2 different times, creating a binary mask that identifies change and not changes based on the mapping function. In our case, this mapping function is the magnitude of the change vector, calculated as the Euclidean norm of the difference between 3 probability class at time 1 and time 2. We also employed an iterative algorithm to define an optimal threshold, resulting in a binary map that distinguishes between changed and unchanged areas. Next, please. Okay. We also compare our method to other available models. For this case, we test a unit model in the upper side, trained for detecting changes in Ukrainian forest using Sentinel-2 imagery. Evaluations on tests in Córdoba region demonstrate that our CVA approach in the bottom side achieves good performance and consistent results. Next slide, please. Okay. To enrich our deforestation mask, we incorporated differentiated spectral indices. After testing across test areas, we defined an optimal threshold for indices related to vegetation health, like NDVI, SAVI, moisture content, NDMI, and burn severity, like NBR. As shown in these images, integrating these differentiated indices improves detection results comparing to using just CVA method. Finally, the next slide, please. The improved deforestation map is presented here. Okay. David, can you present? It's your turn.
Sure. So here are the final results that we tested on 4 different images captured at different times. And here is one such result. So as you can see that the red area highlighted here shows that deforestation did happen, and it's able to capture in much more detail as because of the changes in the vegetation indices. Next slide, please. And here you can even see that the small red area side by the polygon, which is normally hard to detect even from the normal eyes, this with the help of indices, we are able to capture even that. Next slide, please. And it's even able to detect more the difference between the grasses, as you can see highlighted in the light green color at the bottom of the image. And even between the dark area normally highlighted, that indicates the forest and the deforestation here. So this is the area, and it's able to highlight even it here. These are a few of the success cases that we have presented here based on our change detection model. Yeah.
Hi, I'm Flo Caro, and I led the backend and Redis team. We had several collaborators for this team. Some of them were Suraj, Radhika, Svetina, and Francisco himself. Next slide, Francisco, please. In the backend, we had 2 focal points. On one side, we had the core components, and on the other, we had extended components. The core components of the backend, which require application development besides the initial settings, were the queue service, for which we use Celery, and the API gateway, which was fast. We used as framework Fast API. Redis could be considered perhaps a supporting component here. I forgot to change that. We had contributions from Francisco providing some core and initial architecture for the API gateway. Then Svetina was experimenting with rate limiting capabilities. But one of the main works that we had in this team was perhaps learning how to use Celery, because none of us were familiarized with that framework. So we all were experimenting with it. But the good news is that after several weeks of experimentation and work, there was some results regarding the integrating the code from other tasks, like the modeling and the pre-processing task into the Celery side of the backend. So we could get to test a little bit with that. But of course, we need to keep experimenting with that, because the integration was not fully finalized, not even with a specific chosen model that the modeling team had chosen. The part of the extended components did not require application development, so the approach was to experiment with settings in that case, and to see if we could get further control on how the components work, and how that allowed us to test and monitor the core components. Now, yes, next slide. In parallel to this components development, we had set for purposes of experimentation a virtual machine. This was created to test in a cohesive environment where all the components work together, similar to a production one. The initial setup included 1 CPU, 1 gigabyte of RAM, and 10 gigabytes of disk space. perhaps trying to mimic one of the cheapest or simple AWS EC2 instances that are available these days. But for example, things that like the disk space, even with a small setup without final components in it, we found that the disk space ran out fastly, so that had to be expanded, which is not a problem itself, but a consideration to perhaps adjust what instances of Amazon Web Services, for example, would be needed if this went to production in such environment. Then the services approach was running using microservices. We use Docker for the containerization of the applications, and Docker Compose as a deployment solution to get the services running. In the graphic that is there on the screen, we can see the flow of the components and how they interact with each other. But also, in order to show this with a little bit more realism, there's a short video where we can see some of these interacting in a more graphic way. So I will ask Francisco to play the video. First, this is the virtual machine terminal, and we see that the Docker service is running in this screen. Then this is, we are going to see flower monitoring, where you can see the current settings, perform some manual actions, as scaling workers or check task status, among other options. Then we are on the API gateway. We used, for testing, we used the Swagger user interface, where we changed a task, which is a square number task, very simple to just to display this. Then picking up the task ID, we can see the status of the task, and now we can see what result the task got, again using the ID for the task. And as you can see, we have 25 there. And then back to the flower monitoring, we can see, for example, the result on the status of the task, and then we could see the status of the worker. And this is an example of how some of the capabilities one of the components has, which is the Minio object store, and some of the options in the dashboard, for example, how many of the buckets are online. In that case was one only because no more was needed, and how much of the disk space that was using. So just to get a brief idea of how we can perform some monitoring and follow up some values using a user interface. But of course, most of these components also provide an API where we can gather values directly from code too, if we want to build a different solution over pipe. That will be it from my side. Thank you very much.
Thank you, Flo. Amazing. Okay, just as final words, this was a 2-month project, full volunteers working in this in his free time. And in those projects, the more difficult part is understanding between humans. And I think we achieved that part because it's really difficult to work. We've been starting like 80 persons working in this, then we reduce, but all connections between humans are difficult, are challenged. We are from different cultures, from different time zones, and we managed pretty well. We did amazing teams, and yeah, that's the meaning of life, basically. Know person as you that you like. So thank you everyone to